then we can do the quantization right away. And that's why we want to do that. So for Hamiltonian mechanics, it is very similar to the Lagrangian mechanics. But let me don't write this. It has the independent variables is no longer the coordinate and the velocity, but it is still the generalized coordinate. So same as the Lagrangian mechanics. So its independent variables are the generalized coordinates. So again, we have qi, right? In case you forgot, maybe q1 equal to x, q2 equal to y, q3 equal to z, right? Okay, but its independent variable, another one is not the velocity but the momentum, which we just discussed, is pi, no longer q dot I. Okay, that's the first thing. But you need to remember, how do we get pi? It's not m times v, it's partial L partial qi dot. So you do need to know the Lagrangian in order to find the momentum, the generalized momentum. That's why we need to learn the Lagrangian first, right? So in general, then we define something called Hamiltonian. Define. This again is definition. Hamiltonian. Earlier we used something called Lagrangian, right? But now we define something called Hamiltonian. Which is H. It is defined, of course, as we said, it depends on the generalized coordinates q1, q2, but p1, p2 instead of q1 dot and q2 dot, right? And then of course depends on t. But how do we define it most explicitly? It's defined as summation I, pi, qi dot. It can be very confusing, but once you try a few of them, then you will understand. Now, Lagrangian equal to kinetic energy minus potential energy. But Hamiltonian, you cannot just say, let me find the kinetic energy and potential energy and add them together. You need to use this equation. But very often, this is just equals to the kinetic energy plus the potential energy. Okay, so you need to be careful about this. Or how to say, you cannot, maybe I'm not good enough on this, right? You cannot just use your typical understanding of the kinetic and potential energy and add them together. Okay, maybe I should come back again later. I should say that, actually I forgot to say one thing. When I say this Lagrangian equal to this, actually it is not unique. You can come up with many different forms of Lagrangian. You can guess. And then usually you can guess what is the kinetic energy, what's the potential energy, how to define that. You only check it to be correct if the equation of motion, right? So this is the equation of motion, is correct. After you plug in this Lagrangian into this Lagrange equation, you come up with the equation of motion. If it does not align with your experiment, then it's a wrong Lagrangian. But there can be many Lagrangians that give you the correct equation of motion. Then they are all okay. But when you go to Hamiltonian, you need to use this method to find the Hamiltonian. that you first have the Lagrangian, which will give you the correct equation of motion, and then you go through this equation. So what does it mean? It means you go through all the independent variable, independent velocity, degree of freedom, you have the momentum times the velocity. You sum them up and minus the Lagrangian, then that is your Hamiltonian. Right? We will look at an example. Probably now it's still very confusing. But maybe I even did not say it well or even say something wrong. But the main point is, remember, you need to follow this approach. Get the Lagrangian first. And usually, kinetic energy subtracts the velocity. And it should give you the correct equation of motion. And when you go to Lagrange Hamiltonian, then you need to follow this equation strictly. Do not come up with your own. Okay? With this, then the equation, then we have something called Hamiltonian equation. Like the Lagrange equation, right? So again, it has a pair of it for each independent variable. So it says that Pi dot equals to minus partial H partial Qi. Qi dot equals to partial H partial Pi. So there are some criteria for this one, but let's just take it for granted because I forgot whether it should be conserved. This is based on the fact that energy is conserved. If the energy is not conserved, you don't have this equation. But this is the Hamiltonian equation. So if I remember correctly, unfortunately, I don't have it in my cheat sheet. This comes from this, right? I will erase it just so not to. dH dt equal to 0, right? If the energy conserved. And this becomes partial H, partial Qi, dQi dt plus partial H, partial Pi, dPi dt equal to 0. But I'm not going to test this, but for those who are interested, I think I'm right, I forgot. But if the energy is conserved, dH dt equals 0. H depends on the coordinates and also momentum, right? So when you do this one is equal to this, right? Because you just go through the train rule. This is just it. And how can you make this 0? You actually have many choices. One choice is that you get dPi dt equals to negative H dQi. Right? If this one equals to negative of this, and this one equal to this, then add them together, you will get 0. So there are different choices, but they came up with this. Now that is one of the origins. So some people may actually, in some formalism, maybe this is negative is here. Right? But this makes more sense if you go through the math. So I just let you know about this. I'm going to erase it. Anyway, that is not what we want to learn. Our goal is to understand for Hamiltonian mechanics, we also have Hamiltonian equation. So we will do the same thing, right? Let's try to use any questions so far? I think the best is to do some math, right? So let's, in the last few minutes, let's finish the free particles question. So again, I have X equals to Q. And then, of course, the velocity equal to Q dot, right? How about the momentum? Do not just say equal to mq dot, although it is the case here. But we want to use the definition is partial L, partial Q dot. Is that okay? And what is L? We already learned L from the previous slide, from slide 8, right? L is 1 over 2 mq dot square. We already proved that, right? So from slide 8, L equal to 1 over mq dot square. So as a result, P equals to partial 1 over 2 mq dot square partial q dot. What is this? mq dot, thank you. Which is mv. It is expected, right? Good that it is correct, but it's not always, I mean, you need to follow this methodology, okay? This is very important. And from here, I also want to further find out what is q dot. Q dot equal to p divided by m, which I know already. Velocity equal to momentum divided by m for a particle, right? But it's not always the case. Do not use this equation for other condition, right? So what is Hamiltonian in this case? It is equal to summation I equal to 0, right, to whatever, to all the coordinates, pi, qi dot minus L. This is this equation I put up here. Sum over all the coordinates. But how many coordinates do I have? Let me do not call it I equal to 0, just sum them over. How many coordinates do I have in this case? 1, right? Because this is a 1D. Maybe I should emphasize this is just a 1D, right? This is a 1D particle. So because of this, I have only P, Q minus L. Because this is 1D. Yeah. Oh, sorry, PQ dot. I'm sorry. PQ dot. Good point. It's PQ dot. Yeah. Now, I do not want Q dot because, as I said, Hamiltonian has the coordinates and momentum as its independence variable. I need to replace Q dot. But I already found what is Q dot earlier. It's P over M, right? So this is just equal to P times P over M minus the Lagrangian, which is 1 over 2 M Q dot. But again, I do not want Q dot. I want P over M squared. Right? This is Q dot. Right? It's minus L, but L is 1 over MQ dot square, right? So 1 over 2M, so 1 over 2M. Q dot square become P over M square, which makes sense from what we learned earlier. I mean, from elementary physics, right? So this gives me what? 1 over 2. What is this? P squared divided by M, right? Which is correct. It is a free particle. No, not correct. This is the Hamiltonian. And it happens to be the kinetic energy or total energy, right? Or total energy. Maybe I should not write. This is just its total energy. P squared divided by M, right? Okay, anyway. Now, then I will start use the Hamilton's equation, right? So equation of motion. First, I know P dot equals to minus partial H partial Q. What is partial H partial Q? It's partial 1 over 2 P squared divided by M partial Q, right? What is this? Again, what are the independence variable for Hamiltonian? Momentum, P, and coordinate. So I already expressed them in independence variable. What is this value? 0, because I don't depend on Q, right? So this is 0. How about Q dot? This is another equation, partial H, partial, did I say something wrong? Partial P. If I do this, it's just partial 1 over 2p squared divided by m divided partial p, which is equal to p divided by m, right? What does it tell me? It says that the momentum is constant for a free particle. Great, that's what we know, right? It also tells me the momentum equals to m times velocity. Now, momentum is constant. It also means that there's no acceleration, because another formula for acceleration is equal to, is that right? MA, no, and force. Force equals to MA equal to P dot. The change of momentum is equals to, the rate of change of momentum equal to the force, right? If I hope that I'm right. But anyway, this is what a free particle is supposed to be. So again, using Hamiltonian mechanics, I get all the basic things that I expect, right? So next time, let's look at it from another angle, from another example. Okay, we can stop here. Any questions for those online? If not, I will stop now.